People often talk about inverse trig functions, but that's nonsense. The trig functions aren't invertible. Look at y equals sine x. Sine sends different input values like 0, pi, 2 pi, 3 pi to the same output value of 0. So how are you going to pick the inverse for 0? To get around this problem, we're only going to talk about the inverses of trig functions after we restrict their domain. Here I've got a graph of sine, and you can see this function is not invertible. It fails the horizontal line test. But if I restrict the domain of sine to just be between minus pi over 2 and pi over 2, this function is invertible. And here's its inverse, arcsine. By convention, arcsine outputs angles between minus pi over 2 and pi over 2. And also by convention, arccosine outputs angles between 0 and pi, and arctan outputs angles between minus pi over 2 and pi over 2. Note that I'm calling these inverse trig functions arc whatever, arc cosine, arc sine. One reason to call these things arc cosine or arc whatever is because of radian measure. If this is a unit circle, then the length of this arc is the same as the measure of this angle in radians. That's the definition of radians. So to say that theta is arc cosine 1/2 is just to say that theta is the length of the arc whose cosine is 1/2. Now, what happens when we compose the inverse trig functions with trig functions? Before complicating matters by thinking about trig functions, let's think back to an easier example, the square root and the squaring function. And just like trig functions are not actually invertible, the squaring function is not invertible because multiple inputs yield the same output. So we had to define the square root to pick the non-negative square root of x. And that means that if x is bigger than or equal to 0, then I have the square root of x squared is equal to x. But if x is negative, this is not true. The same sort of deal happens with trig functions. So if theta is between minus pi over 2 and pi over 2, then arcsine of theta is equal to theta. But if theta is outside of this range, this is not the case. If theta is outside of this range, yes, arcsine is going to produce for me another angle whose sine is the same as the angle theta, but there's plenty of other inputs to sine which yield the same output. Things are even more complicated if you mix together different kinds of trig functions. For example, the sine of arctan of x happens to be equal to x divided by the square root of 1 plus x squared. Where would you possibly get a formula like that? Well, the trick is to draw a right triangle, the correct triangle. Well, here I've drawn a right triangle, and I've got an angle theta, and I've drawn this triangle so that theta's tangent is x. That means that theta is the arctangent of x. Now, by the Pythagorean theorem, I know the hypotenuse of this triangle has length the square root of 1 plus x squared, and that gives me enough information to compute the sine of theta. The sine of theta is this opposite side, x, divided by the hypotenuse, the square root of 1 plus x squared. This tells me that the sine of arctan of x must be x over the square root of 1 plus x squared. Drawing pictures will get you very far in understanding all these relationships. I think it's basically impossible just to memorize all of the possible formulas that relate inverse trig and trig functions. But if you're ever wondering what those formulas are, you just draw the appropriate picture and then you can figure it out right away.